if you believe the propaganda of the previous lecture, then you, like me, would your earnest desire would be to study simplicial complexes up to homotopy. And the most important step here is to understand a very special class of spaces which are contractible. And here's the definition. A topological space X is contractible if it is homotopy equivalent to a point. And of course, for us, a point is the geometric realization of the solid zero simplex. This is the most important thing to keep track of when you're trying to prove homotopy equivalence. If you have a large database in your head of contractible spaces, that's extremely helpful. And so we'll try and build pieces of that database over this lecture and the next few. But for now, let's sort of drill down to the definition. What does it mean for a space X to be contractible? Well, it has to be homotopy equivalent to a point. So let's think about what that means. There exists a continuous map F from X to point. Do we have to think very hard about what that map has to be? No, there's a unique map that does this. It sends every point in X to the one point. That's it. And there exists a continuous G from this point back to X. Now this one, there are tons of choices. In fact, you have as many choices as you have points in X. You just pick out one of those points. And let's say the image of this map is G. Of this map G is P. So it takes that one point that you have and sends it to the point P in X. And it cannot have a bigger image because it only has one point to play around with. Okay, so these two maps have to exist. Well, the first one always does if X is not empty. And the second one is just picking out a point in X, which you can also do if X is not empty. And you want F composed G to be homotopic to the identity somewhere, and you want G composed F to be homotopic to the identity somewhere. And if I've done this correctly, this one is to point, and that one is to the identity on X. Now, if you think about it for half a second, you will realize that doing G and then F sends the point to itself. There's nothing fancy going on there. You take the point, you send it to P, and then you're forced, because P is part of X, everything goes to the point, you send it back to the point. Therefore, in fact, this first condition is telling you nothing useful, because F composed G is in fact equal to the identity on the point. So there's no need to think about a homotopy. They're literally the same map. This one takes some thought. You have to think about that a little. So what this means, look at the left side. You first apply F. You send everything in X to a single point, and then you send that point back to P in X. So this is the constant map X to X, sending everything to P. So what we have shown is that X is contractible if and only if the identity map 1x is homotopic to a constant map X to X, sending everything to some point P. And this is a useful criterion. It's equivalent completely to the definition. So basically, you can either show a space is contractible through some other means, or if you want to change the definition, what it means is you can find a homotopy from the identity map to a constant map. Okay, good. Let's see some examples of contractible spaces, and I'm not going to prove any of these are contractible. We will, at least I'm not going to prove it right now. We're going to build the tools we need to prove these are contractible later. But it's important to start storing them away. You will need a large database of contractible spaces in order to use the tools that we're going to build. Okay, so one example is for all k bigger than or equal to 0, the solid k simplex, which we've called delta k, is contractible. Okay, good. Another example, or another family of examples, because this is an infinite family of examples, is for all simplicial complexes k, the cone, which I'm going to write it like this, is contractible. Okay, in these videos I have not defined what the cone over a simplicial complex is, so you have to read the lecture notes for week 1 to see a definition for what the cone over k is. Whatever that definition is, no matter what k you use, the cone over that k is contractible. And finally, every tree, and by tree I mean connected graph with no cycles, is contractible. So tree might look like this. This is a tree. What I'm not allowed to do is draw that gray edge, because if I draw that gray edge, then there's going to be a cycle, and that's not allowed. What I'm also not allowed to do is have a disconnected vertex here, because it has to be connected by definition. Okay, so each of those families of simplicial complexes, so k-simplices, cones, and trees are contractible. And again, we will prove, or at least generate the machinery to prove all of this during the course of week 2 lectures. Okay, the most important immediate property of contractible spaces is a sort of extension property. Let me write this down here formally. So if X is contractible, then for any dimension k bigger than 1, any continuous map from the hollow k-simplex to X can be continuously extended to a map from the corresponding solid k-simplex to X. And of course, in both cases, I mean the geometric realizations. And the proof of this statement is for general k, it's by induction, and it's fairly subscript infested. What I'd like to show you here is the base case of the induction, and everything else, the inductive case is very similar, but with more messy subscripts, more or less. So let's do the case k equals 1 here, and I'd like you to think about how to extend it to larger k in the safety and privacy of your own homes. So what does case k equals 1 mean? It means that you have continuous map from the geometric realization of the hollow 1 simplex to X. And remember, the geometric realization is just 2 points. Up to homeomorphism is just 2 disconnected points. So its image is just, I guess we call these points 0 and 1, don't we? So this image is just f of 0, we'll call it x0, and f of 1 we'll call x1. And so the claim I'm making is that the minute I have 2 points, any 2 points picked out in X by this map F, I can find an extension to the of this map to the entire interval 0, 1. So let's see how that would go. So pictorially, you have this point 0, you have this point 1, you have some contractible space X, and you've sent 0 via F to some x0. You've sent 1 via F to some x1. And what you'd like to say is that this entire thing, this interval between 0 and 1, can be sent somewhere in a way that preserves the endpoints. That's what it means to extend F. So we want there exists F plus sending that interval to some continuous curve in X, which is just a fancy way of saying that if X is contractible, it has to be path connected. Any 2 points I find in X, I should be able to find a continuous path. So the question is, how can we build this path from the knowledge that X is contractible? So let's use the criterion we built above. So since X is contractible, there exists a homotopy theta from X cross 0, 1 to X between the identity map and the constant map. X to X, sending everything, sending every point to some P in X. Now, what we are not allowed to do is assume that this P is either X0 or X1. It's just some point in X. We have no control over what P is. So let me draw the cartoon for what is going on here, and hopefully with that cartoon you will be in good shape. So here's X. Let's draw it again. Here's X0. Here's X1, and somewhere is a P. And again, it's not safe to assume that it's one of these 2 points. So if you look at theta x t for t between 0 and 1. So this goes from identity to P. But the identity map, look at theta x0. So when t equals 0, then theta x00 is just x0, because it has to be the identity map. And when t equals 1, theta x01 has to equal P, because everything gets sent to P map, which is a silly way of saying that there is a path. So this path is theta x0t for t between 0 and 1. And similarly, for exactly the same reason, there's some path which starts at x1. So this is theta x1t for t in 0, 1. This is just because we are given the knowledge that X is contractible, so there is some P somewhere, so that the identity on X is homotopic to the constant map sending everything to P. And now you see what we have to do. We have to combine these paths to build this concatenated path that goes from x0 to x1, and solves the problem. So if you want an explicit formula for that path, that's where this thing has to go. It has to go to this concatenated path. If you want a formula for it, you can go read the lecture notes, but that's the basic idea. And you can do this every dimension. If you had a hollow triangle, then you could fill it up so that P was the very center of the, P is where the exact middle of that triangle goes. Okay, so this is a fairly useful criterion, which we will come back to later. In the meantime, there are certain tricks that show up again and again and again. So I think it will be unfair of me to be talking about homotopy and not show you the tricks. One of them, and we'll end the lecture after we see that, is, so this is a trick or a strategy when you want to prove homotopy equivalence, is to show that f, g going from x to y are homotopic for y living inside some place where lines make sense. So the standard example is Rn. Try to use what's called the straight line homotopy. So, which is to say, try theta from x cross 0, 1 to y, which sends xt to t times f plus 1 minus t times g. Now, why did we require y to be in Rn? Because we're taking f of x and we're scaling it by t. F of x is something in y. And so if it wasn't in some space like Rn, then t times f of x would not make sense. So you need some sort of linear structure. And then similarly for g of x, you have to scale it by 1 minus t. And then you have to be able to add them. So this only works where you're allowed scaling and adding. So really you need things to be in a vector space somewhere. Okay. And to see what this sort of trick can do, it can show that one of the examples that we showed of contractible spaces is honestly contractible. You can use a straight line homotopy from the identity map to the constant map, and that class is the solid simplices. So for k bigger than 1, the solid k simplex is contractible. And if you'd like to prove this, let's set it up. The proof goes something like this. So let x0, xk subset of Rn be affinely independent, so that the geometric realization of the thing that we want to show is contractible is the linear combination of I equals 0 to k ti xi, subject to the requirement that the sum of the ti's is exactly 1, and each of these individual ti's is bigger than or equal to 0. So that's the definition of the geometric realization of the solid K simplex. Okay, so what's the identity map? It sends this sum of ti xi to itself, and pick any vertex you like. I like x0, so let f from this delta k to itself be the identity map, which I'm not going to say anything about because it just fixes every point, so that's kind of boring. And let g, again from delta k to itself, be the map sending all points to our favorite vertex, which for me is x0. You can choose x5 if that's your thing, or you can choose xk. It doesn't matter. Okay, so pick one of these vertex. And so the straight line homotopy, SLH, is prescribed by the formula theta goes from del k cross 0, 1 to delta k, and we have to check that it satisfies these rules, but it's really going to be theta xt is t times f of x plus 1 minus t times g of x. So so there are three things to check. The first thing to check is that at t equals 0, you get the constant map, which you do because the first term will disappear. At t equals 1, you will get the identity map because the second term will disappear. And so really, what you want to show here is that this linear combination, tfx plus 1 minus tg of x, if you feed it an x in the geometric realization, and you feed it a t in 0, 1, always spits out. The stuff on the right side is always living in the geometric realization of delta k. That's all. That's the sort of challenging part. So what I want to say is clearly theta x0 equals f of x, g of x, and theta x1 equals f of x. So this is fine. Want to show that the image of theta xt lies in delta k. And to do this, you let x be one of these combinations, ti, xi, going from 0 to k, and you let t belong to 0, 1. And then note that theta xt is t times, now f was the identity, so it's just going to give you this 0 to k, ti, xi back, plus 1 minus t times x naught. That's g. It sends everything. It doesn't matter what x is, it's going to give you x naught. Okay, so let's collect the coefficients. On the left side, you have all of them added up. So t times ti, xi. On the right-hand side, you only have x naught. So you should collect the x naught terms together. So and the non-x naught terms together. So this is going to be t times sum from 1 to k, ti, xi, plus 1 minus t x naught. And what are we missing? Well, plus t times t naught x naught. Okay, so if you want to collect all of the x naught terms together, so this is, in fact, let's move the t in. So this is sum of t times ti times xi. Now starting at 1, going to k, plus, oh dear, let's see, this is x naught times 1 minus t plus t times t naught. That's the linear combination we get. And if you simplify it a little bit more, just a bit, not too much, you still have t, ti, xi plus 1 minus t, and then the quantity is 1 minus t naught, x naught. And now, if you remember, sum going from 0 to k of ti, xi, sorry, not the xi, just the ti, this had to be equal to 1, which is to say that 1 minus t naught is the same as the sum from 1 to k of the ti. So if you replace this with sum 1 to k of ti, you will realize that the coefficients still sum to 1. Because on the left side you have TTI, and on the right side you have 1 minus TTI. And so if you add all of that up, you will get 0. And that's the end of the proof and this lecture.